Hi everyone. Today we are going to study shortest spanning tree. Now before we study shortest spanning tree, let us do a quick revision of spanning tree. So a spanning tree in a graph G is a minimum or a minimal subgraph connecting all the vertices of G. We have already studied this, and you know that a spanning tree is a subgraph of a graph G, which is a tree. Such a subgraph, which is a tree and which covers all the vertices of that particular graph, is called a spanning tree. That is the reason it is called a minimal subgraph, and it connects all the vertices, or it covers all the vertices. So any such subgraph of a graph G, which is a tree and it covers all the vertices of the graph G, is called a spanning tree of the graph G. If a real number is associated with each edge of the graph, now we have seen graphs which do not have any numbers associated with the edges. But if a number is associated with every edge of the graph, that is, a real number is associated with every edge of the graph G, then such kind of a graph is called a weighted graph. That real number is also called the weight of the edges. For that reason, we call it a weighted graph. So what is a weighted graph? Any such graph which has a real number associated with all of its edges. Now the weight of a spanning tree T of a graph G is defined as the sum of the weights of all the branches of the spanning tree T. Now if the graph has the spanning tree as its subgraph, in that case the weight of the spanning tree will be the sum of the weight of all the branches of the spanning tree. This graph G may have different spanning trees, and these different spanning trees of the graph G will have different weights. Now, among all the spanning trees of the graph G having different weights, the one spanning tree with the smallest weight is called the shortest spanning tree, or the shortest distance spanning tree, or a minimal spanning tree. And this is what we are going to study today. That is how we find the shortest spanning tree. So now I think you're clear with the concept. We have a graph G. This graph G has a subgraph which is a spanning tree. Now this graph G will have more than one spanning tree. As we all know, any graph G has more than one spanning tree. Now this is a weighted graph. That means this graph has a weight or a real number associated with all of its edges. So if the graph is a weighted graph, that means the spanning trees of this graph will also be weighted. That means the branches of all the spanning trees will also have a real number associated with them. And what is the weight of the spanning tree? As I just told you, the weight of the spanning tree thus will be the sum of the weights of all the branches of that particular spanning tree. And for this reason, different spanning trees will have different weights. Now, out of all these spanning trees, the one with the smallest weight will be called the shortest spanning tree. So that means among all the spanning trees of the graph G, one with the smallest weight is called a shortest spanning tree, and you may also call it by the name of shortest distance spanning tree or minimal spanning tree. Now, how do we find the shortest distance spanning tree, or the shortest spanning tree, or the minimal spanning tree? Basically, there are two primary algorithms for finding out the shortest distance spanning tree, or the shortest spanning tree. One is your Kruskal's algorithm, and the other is your Prim's algorithm. We are going to study both these algorithms to find out the shortest spanning tree, and in today's video we will study Prim's algorithm. Now let's see how using Prim's algorithm we can find out the shortest spanning tree in a graph. So if this is a connected graph, now obviously a spanning tree will be found in a connected graph only. We all know that. Now this is a connected graph G. Now this connected graph G has several spanning trees. I am not interested in finding out all the spanning trees. I am interested in finding out only the one with the shortest weight, one with the minimum weight. That means I am interested in finding out a spanning tree which is a shortest spanning tree. So how do we go about finding the shortest spanning tree? You can start with any vertex. Here I start with vertex A. As I said, you can start with any vertex. It is completely your choice or your call which vertex you want to start with. I start with vertex A, right? Now I will see which are the vertices, which all vertices are directly connected to the vertex A. Clearly you can see there are three vertices, vertex E, vertex B and vertex C, which are directly connected to vertex A. Out of these three vertices, which is the one with the shortest weight? The cost of reaching from vertex A to B is 5. See, this real number associated with this edge is its weight, which is 5. And what does it represent? This represents the cost of reaching from this vertex to this vertex. So these are all the weights I'm talking about. 15 is the weight of this particular edge, 5 is the weight of this particular edge, and 10 is the weight of this particular edge, and so on. And what do these weights represent? These weights represent the cost of traveling from one vertex to another vertex. Like the cost of traveling from vertex A to vertex B is 5. Right? The cost of traveling from vertex A to vertex E is 15. The cost of traveling from vertex A to vertex C is 13. Since I have chosen A as the starting vertex, that means I started with vertex A, and I am supposed to find out all those vertices which are directly connected to A. You have several other vertices also in this graph, but I will not consider the vertices which are not directly connected to A. Like D, you can see here is not directly connected to A. So I will only consider those vertices which are directly connected to A, and those vertices I can clearly see are E, B and C. Now, out of these three vertices B, E and C, I have to see that starting from A, what is the minimum cost of reaching to any other vertex. Now, you can clearly see the cost of reaching from A to E is 15, the cost of reaching from A to C is 13, and the cost of reaching from A to B is 5. So, clearly the minimum cost of reaching from A to any other vertex is 5, which is from A to B. So I will choose this vertex. So the path A to B and the cost is 5. Now among A and B, again I will find out all those vertices which are directly connected to A and B. Earlier there was only a single vertex A, so I was considering only the vertices which were directly connected to A. Now we have two vertices in picture, A and B, and I am going to consider all the vertices which are directly connected to A and B, and among those vertices the one with the minimum cost. So the vertices which are directly connected to A have already been considered, right? Now let's see the vertices which are directly connected to B. They are D and C, right? And the vertices which are directly connected to A are E and C. So the cost of reaching from B to D is 8. The cost of reaching from B to C is 10. the cost of reaching from A to C is 13 and the cost of reaching from A to E is 15. So clearly the one with the minimum cost is from B to D. So I will choose vertex D. I will choose this path from vertex B to D, right? Now I have 3 vertices in picture, so I will consider all those vertices which have not been visited till now and which are directly connected to vertices A, B and D. So again, the vertices which are directly connected to A are E and C. Vertices which are directly connected to B are C. D has already been visited, so I will not consider D. Are C. And the vertices which are directly connected to D are C. The same vertex B has already been visited, so I will not consider B again. So out of all these vertices, that is E, C and again from D, C, which is the one with the minimum cost? It is from D to C with the cost of 6, right? So I will consider the vertex C with the minimum cost of 6 because from A to E the cost is 15, from A to C the cost is 13, from B to C the cost is 10 and from D to C the cost is 6. So this is the one with the minimum cost. That is why I chose vertex C from vertex D, because from vertex A the cost of reaching to vertex 6 was 13. From vertex B the cost of reaching to vertex C was 10. From vertex A the cost of reaching to vertex E was 15. And from vertex D the cost of reaching to vertex C was 6. So this was the minimum cost, hence I chose this. Right, so from D to C the minimum cost is 6, so I draw it like this, the edge that is going from D to C with cost 6, right? Then next we have 4 vertices in picture now, vertex A, B, C and D. With all these vertices, I will see all the vertices that are directly connected to 4 of them. So the one directly connected to A is E. The one directly connected to B is A, C and D, but they have already been visited. I will not consider them. The one directly connected to D is B and C, but they have already been visited, so I will not consider them. The one directly connected to C are A, B, D and E. Now out of A, B, D and E, E is the only one which has not been visited because A, B and D have already been visited. That is why they are here. So that means E is the only vertex which is left. Now there are 2 edges which lead us to vertex E. One is from A to E and other is from C to E. So again in this case also we have to see which edge is with the minimum cost. The cost of reaching from vertex A to E is 15 and the cost of reaching from vertex C to E is 20. So obviously 15 is the minimum cost out of these two. So we will draw an edge from A to E because it has minimum cost. And this way we get our spanning tree, which we call our shortest spanning tree. This way we can find out the shortest spanning tree using your Prim's algorithm. So from this connected graph, I have found out the shortest spanning tree using Prim's algorithm.